Okay, picking up in chapter 20, we're looking at the MBA programs example, and we did step 1 for the null hypothesis is that the true mean in-province annual tuition, so the average is 30,000 for all MBA programs, versus the alternative hypothesis is the true mean is greater than, because of the keyword more, so greater than 30,000. So we have here a one-sided t-test. Our n in this case is equal to 20 because there's 20 MBA programs, and our degrees of freedom then would be 19. So the test statistic is equal to 36,625, subtract 30,000, divide by 24,645, divide by square root 20. That gives us 1.202. From there, we calculate the p-value from the t-table, and we get a p-value between 0.1 and 0.15. Okay, looking at the t-table, that was determined by looking at the degrees of freedom column, which we find 19, and then we look at that 19 degrees of freedom row, and our test statistic falls between these two values, 1.066 and 1.328. We then scroll down to find the one-sided p-value, the corresponding values, and we can see it's between 0.1 and 0.15, or 10 and 15%. So the question is the p-value range less than 0.05? And the answer is no. So therefore, we cannot reject the null hypothesis. If the p-value range was greater than 0.05, that's our cutoff, right? It's our significance level alpha, then we would then reject the null hypothesis. But in this case, we can't, because we have the p-values between 10 and 15%, which is more than 5%. So that means that there is that we can accept, or we accept the null hypothesis because we cannot reject it. So this is what holds right here. So there's no change. Our last topic for this chapter is the match pairs T procedures. So this is when we look at two columns and we take the differences and then we boil it down to a one sample test statistic using paired data. So looking at an example on identical twins, and this study comes from the citation here. And so this study did all kinds of different tests, including the difference between the IQs between the twin pairs. And so there was 10 pairs of twins, and the one here was the first twin born, and this was the second twin. And you can see in the box plots that there's not a lot of difference between their IQs, but we run the test anyways to see about statistical significance and see if this is a formal test to know for sure. So what we do is we have the firstborn, that's 1, column 1 there, and subtract. So we take column 1 and we subtract column 2 to get column difference. So that column is going to be the difference. So 96 subtract 89 is 7, 87 subtract 87, 0, 101 subtract 103 is -2, and so forth. Then you just look at the difference column and you get the sample mean, subscript D, and the sample standard deviation, subscript D. Subscript D stands for difference. And the box plot here is just the difference in IQs between the twin pairs. So our n in this case is 10, and our degrees of freedom would be 9. And so if the sample mean is calculated to be -1.2, and our sample standard deviation is calculated to be 8.36. This was step 1, the null and alternative hypothesis. So it's always equals to 0, because that means for the null hypothesis, it's a statement that means there's no difference between the two. So it just means no difference in this case, no difference in IQs, versus the alternative hypothesis, which is does not equals, that means there is a difference. Step 2 is the test statistic, and then that plugs in all those values to get negative 0.454. Step 3 is calculate the p-value. It ends up being greater than 50%, which is quite large. That means we have very, very weak evidence against the null hypothesis. So that means that we cannot reject the null hypothesis and conclude that there is no difference in IQ scores between the pairs of twins. Okay, so moving on to our last example is the psychology example. So there was a clinical investigation to assess the repetitive behaviors of children affected with autism. So there was 10 children enrolled in the study with autism, and there was 10 controls where there were healthy children not diagnosed with autism, and they were matched with age and gender, and which can be confounding factors in the study. So they're matched to do a matched pairs design, and then a matched pairs hypothesis test. So each child was observed by the study psychologist for 3 hours, and the repetitive behavior is scored on a scale between 0 and 100, and those scores represent the percent of the observation time in which the child is engaged in repetitive behavior. Each subject in the experimental group was matched with a subject in the control group, as we said. So column 1 here is the children with autism. Column 2 are the healthy controls. So we take column 1, subtract column 2 to get the difference. Then once we get all the difference for each row, we then calculate the sample mean of the difference. So that's taking all of the differences here, all of these values here, and we get the sample mean. Subscript D is 16, and the sample standard deviations, so that's S subscript D, is 18.97, and those are used for the test. Step 1 in the test is state the null and alternative hypothesis. So that means the mean difference is equal to 0 versus it's greater than, because of our keyword. So greater than is part of the question. Using a significance level, that's alpha, 5%. So step 2 is the test statistic. We plug those values in and we get 2.67. That brings us to the t-table. You can look this up, this value on the t-table on 9 degrees of freedom, and you'll see that it corresponds to a one-sided p-value. It'll be a one-sided p-value from the table between 0.01 and 0.02. So since the range is less than 0.05, and it can be less than or equals, we then conclude that we reject the null hypothesis. In this case, we conclude that there is a difference between the scores, between the two, between the children with autism and the healthy controls. And we conclude that because it's greater than, we conclude that the scores for the children with autism, the repetitive behavior scores for them, were higher than the healthy controls because of the way we did the test. We did 1 subtract 2. So we did the children with autism 1 and then subtract the healthy controls children. That's column 2, and that's our conclusion. And the last I will leave for you. This is about robustness in the T procedures, and more talking about bootstrap methods and permutation tests that go beyond the course, but you may see them in other research methods type courses in the future.